In the following videos, we will examine database recovery. This video gives an introduction to the overall problem. So what is a problem? The question we're looking at is, what happens if any error occurs while operating the database system? Well, what is an error? An error might be something like a power failure. What happens if electricity is failing for whatever reason? Then, of course, there might be situations like you have dirty pages in your database buffer, dirty pages, containing changes, containing updates from committed transactions. And if those changes haven't been written to disk yet, then you might be losing those changes. That's a problem. That's violating the D in the asset properties. D is then violated. We will look at that in a moment in more detail. It's definitely a problem. You might be losing changes in such a case. And power failures may have multiple reasons. Maybe it's just a failure for a few milliseconds and seconds, and then once the power gets back, you're able to restart the database server. But of course, you may also have more severe incidents like a fire, flood, earthquake, tsunami, or burglary, some guy breaking into your data center and stealing your server. Then there's no way to restart the server. But still the question is, what happens with your data? So in these severe scenarios, sometimes using forensics, you're able to recover data on hard drives. So even if there's a fire, even if water invaded your hard disk, sometimes you're able to recover the data, but it's an expensive process. Hardware errors. So hardware errors in the general case, but also cases like a hard disk crash. And this means the disk arm crashes on the platter. This basically ruins your hard drive and you won't be able to restart your hard disk. Again, forensics may help here. For this, you need forensics, data forensics. There are specialized companies where you can send in your hard disk and then they're sometimes able to recover some of your data. Memory failure is another issue that might occur. So memory here means DRAM, main memory. So you write some data to a memory address, but then you're not able to recover the data, or you get something back that is actually wrong, that's different from what you actually wrote to that address. That may also happen on a hard disk, of course. Then all kinds of network problems that may occur, especially distributed systems, that's a concern you should be aware of if you have two servers and let's say somehow communicate. Assume a situation like that. And this connection gets interrupted for whatever reason. So this is server 2, this is server 1. If that gets interrupted, that may be a problem. And then the question arises, what is the impact on the consistency of your database? Well, then all kinds of software errors, be it in the database system itself or be it in the applications using the database system. Or last but not least, unforeseen events like the janitor's dog running through the data center and peeing at your server, stuff like that. All kinds of errors may happen. And the question is, how do we handle these errors? We should be aware that these errors may happen and the database system should be resilient. It should be able to cope with those errors. If you think about these error scenarios, it's clear that those scenarios are not solely important to consider for database systems. For any software that is important, any software that should be up and running 24 hours a day, you should be worried about these scenarios. So recovery is something you should worry about in any software. And you see it here and there in software products. Software products here and there implement some of the recovery functionality we will also later on find in database systems. So the typical thing you find is undo functionality. You see that even in text processors that allow you to go back, to previous versions of your file. That's already kind of a recovery functionality in a way. Many software products also create automatic backup copies. So when you work on a file, they create a snapshot of that file in the background. So usually when you open a file, assume you have a file here, that is your file. Now you open it with an application. So what will the application do? It will first create a copy of the file, which is read-only copy of the file. And once it created that copy, it will allow you to change this file. This is a very important process because if anything goes wrong while writing this file, you might be losing the entire file. If in that situation you don't have a copy, and an older copy is just fine, any copy, an older version of the file, you lose all of your data. So you typically work on a version that can be edited, and you create snapshots in the background. So every few seconds, every few minutes, the software will create a new copy, a new version of the file. So if this is version 1, this will create version 2 eventually. You will be working on this file in the background. This copy, this backup copy will be replaced by newer versions. That's a very important process in just any software. Then journaled file systems, that's an important class of file systems. So back in the old days, when you switched off the power while operating a computer system, this was a problem sometimes, because then sometimes the file system was in an undefined state. This problem was removed with journaled file systems. Journaled file systems can survive power failures easily. They can easily get back to a consistent state. One problem, though, you should be aware of when looking at journaled file systems is that sometimes they can back to a consistent state with respect to metadata only. So metadata is information like, okay, what's the name of the file, what's the size, what is the path on the file system, stuff like that. But then they're not able to get back to the content. So if you wrote some content and while writing it, there was a power failure, then you still may have a problem in the journal file system. So be careful when using these journal file systems to understand whether they are able to recover on metadata only or also on content. Well, in the very prominent example for recovery failure, actually, you see that in many devices. I've seen it for video cameras. I have a video camera that has this problem. I have a TV receiver that has this problem. Sometimes when these systems update, when the operating system of the camera or of the TV receiver, in my case, is updated, they show a message like that: do not switch off. System is performing XYZ. And this is actually a kind of failure in terms of recovery, because it basically signals if anything goes wrong while displaying this sign, we really have a problem. So this software is not able to recover, basically. Yeah? So what this means actually is will not be able to recover your system into a consistent state, will not be able to recover. You have to try to switch off your device showing this message while that message is displayed. Give it a try. Maybe you have to reinstall the operating system. Maybe you have to reinitialize it to how it was shipped initially. But those are things that could be fixed in many situations if you understand recovery well. Actually, those messages are not required if you do it in the right way. So in the following, we will talk about recovery. That is the important term here. So recovery means we have a mechanism that allows us to get back to a consistent state. Recovery is a mechanism allowing us to get back to a consistent state with respect to an arbitrary software, but also state with respect to the database. And in a database, of course, we have to be more precise. We have to look at these famous asset properties. What does recovery imply for asset? Well, just to recap, what was this asset about? You should know that from the undergrad lecture, but just to have everyone on the same page here. So those are the four properties: atomicity, which means all or nothing. If you have a transaction and it changes something, either all of its changes make it into the database or none of them. That is the A property, very important. Consistency means you have a consistent state preservation. If a transaction starts, it starts on a consistent state, and if it commits, it should leave the database in a consistent state, which also means that while the transaction is operating, it may violate integrity constraints. Just when committing, the integrity constraints should be preserved again. Then, of course, isolation, which means concurrent transactions have the same effect as some serial schedule of transactions. So to an individual transaction, it looks as if it owned the database. Then durability, which means committed changes will never be lost. Once the database told the application, yeah, it's committed, the database must make sure that the changes will never get lost. And this is, of course, a problem for durability. If the database said, yeah, it's all fine, I committed that, and then there's a power failure, well, there might be a problem. There might not be such thing as durability, actually, even though the database told the application that it is durable. So if you're unsure about the asset properties, I recommend that you first get back to those and recap what they are about in more detail. So this is just really a summary slide on a high level recapping what it is about. So what recovery looks at are the A and the D properties. Atomicity and durability, that is what we have to be concerned with here. Isolation is something we look at in concurrency control. This is concurrency control, which is kind of orthogonal to this concurrency control. So we are not touching it here. Of course, it also has some interactions with recovery, but it's mostly orthogonal. So for the moment, we are really worried about the A and the D property here. So let's revisit the different errors that may occur again, because we can classify the errors. So the easiest error to handle is called a local error, which means there's an error or abort in the application program, or there's an abort triggered by the system due to a deadlock. This is something where concurrency control might kick in. This is concurrency control saying, well, I can't figure out how to run this set of transactions concurrently, so some of them have to be stopped, have to be aborted. So the database system itself triggers the abort here. So which means if a transaction is aborted here, the changes done by that transaction have to be undone. So it doesn't matter whether it was the application program, whether it was any error here, whether it was concurrency control aborting the transaction. We have to undo the changes. We have to undo changes of those transactions. So we assume here that the database system is just fine, it's up and running. There was no system failure in that sense. It's just a local problem. One transaction has to be aborted, and therefore it's a local undo, which means we have to remove persistent changes done by non-committed transactions, which is again A. A is saying if a transaction didn't commit, all of its changes have to be undone. If that transaction did any change to the database store, those changes have to be removed. That is what is said by A, and that is what we have to care about. So again, an example to clarify that, assume we have time going from left to right here on this axis. We have two transactions. This is a transaction transferring 100 euros from account A to account B. Here's the second transaction. Let's give them numbers, T1 and T2. So this transaction is transferring 300 euros from account C to account B. Well, then here, this transaction actually committed. That is what the green box is signaling here. This is committed. So we must make sure that the changes performed by T1 become durable. However, here there's an abort right in the middle of running this transaction, which means if this transaction already transferred some data in between accounts or removed money from some of the accounts, all of those changes have to be undone. So this didn't commit, so it must not be persisted. That's not allowed because it would violate the A property. So this is the scenario of a local error. We can do this by a local undo. Remove the persistent changes done by the non-committed transaction. That's the first class of errors. Let's look at the second class. And that is loss of main memory as mentioned above. So here the situation is typically dirty pages in the database buffer are lost. We are still able to restart the database system, but we lost some of the dirty pages. And the question is what happens? Dirty pages may mean, again, what is a dirty page in our world here? Assume we have a page 42. And dirty means the page in the database buffer has a newer version. It's in a different state than the one in the store. So we have a copy here on disk. This is a hard disk, let's say. It's page 42 on hard disk. Page 42 prime is a newer version in the database buffer. And that is why we call it a dirty page, because we did some changes on it. If those changes, assume this was changed, assume this was changed, assume this was changed by transaction 1, assume this was changed by transaction 2, and we lost this page. Well, then there are two things to consider here. This change by committed transaction 1, perhaps this is transaction 1, let's assume it committed, then actually this should have been written to disk. It is not on disk. On disk we will find this page, the old version, without that change. That's not so great because the durability property ensures that those changes should be persisted. The database said it committed when committing that before the crash, but now when we restart the database system, we don't see the change. So this is definitely violating the durability property. The change is not in the store. Yeah, so we have to do something about that. What about T2 if we assume that this one aborted, that committed, commit, abort, well, the change didn't make it to the store. This is actually kind of good because when we restart the database system, we see that change done by T2 is not available on the page. So it is as if it was never done, which is the property we want to have. So this is kind of implicitly okay in this scenario. So in the general case, what we have to do in such a situation when we lose main memory are two things. First is undo. We remove persisted changes done by non-committed transactions. Non-committed transactions. So if for some reason this page was written back to the store, how may that happen? That may happen because the database buffer evicts the page. If you have page eviction here, if you remember when we talked about the database buffer, I did a separate video on that. The database buffer may evict a page, and if it evicts a page that contains a change done by a transaction that then does not commit, we will have a situation as follows. Maybe I write it down again here to not overwrite the other example. So assume again those two pages, P42. This is in the database buffer. This is on hard disk, and now we have page eviction. So maybe I remove it over here. So let's get rid of this one, okay. So now the database buffer is evicting the page. Let's assume again we have those two changes of T1 and T2. It's evicting the page. And now what we have on the store are two things. One is a good thing because that's a change done by T1. This was done by T1, right? So this committed eventually, so it's good. It made its way on the store. This is fantastic. But now here's a problem because T2 aborted and the change found its way to the store, which should not happen because it's violating the atomicity property. This is violating atomicity. This is fine because this change made it to the store. So this also does not solve our problem. In undo, you have to look at this scenario here. You have to make sure that if a change done by an aborted transaction, by a non-committed transaction found its way to the store, you have to get rid of it again. This has to be removed. That is what's happening here. This is what is done here. Remove this stuff again. In redo, you persist all the non-persisted changes done by committed transactions. This is then again ensuring durability. So which means we're in this situation. Here, if this page was not evicted, it was not written back to the store, this means when we restart the database system, we do not find the change done by T1. So it's not on the store. Therefore, in redo, we have to make sure that this change will be applied to the store. So what we want to have is neither this situation here, let's call it situation 1. We don't want to have this one, let's call it situation 2. What we want to have is situation 3, and that is, so we have this page, we have those two transactions working on it, it's page 42. Again, this is in the database buffer. We have it on the store. Let's call it hard disk again as above. So what we want to have in the end is something like that. This change done by transaction 1, that should be in the store. This change that was done by transaction 2 should not be in the store. That is the situation we want to have. And we need to make sure in the database system that we end up in a situation like that when recovering, when restarting the database system. That is the situation we want to have, not anything like 1 or 2. That's not good. Okay, again, a little example here. So similar situation as above. You have two transactions, T1 and T2. T1 is committing, T2 is failing because the power failure happens right in the middle, before transaction 2 was able to commit. So then we have exactly this situation again. This stuff must be committed. Everything T1 ever did must be committed. However, whatever T2 did must not find its way. That is what I explained here with these examples already. So changes done by T2 should be removed. This shouldn't happen. In this scenario, you should have something like this here. So here we must make sure the D, here we must make sure the A, that they are not violated. It's very important, and that is what the database system should ensure. Or any software doing changes to some state must ensure these properties, or should ensure. But in a database system, it's super, super important. Okay, finally, a severe case that may happen, of course, it's the third case. So the first was a local error, the second was loss of main memory. A really severe case is loss of external memory or storage, or even the entire server. But of course, you can get back to buying another CPU, installing another version of the software. That's an easy case. But getting back to your data once you lose external storage, that might be really difficult. So assume the database store and/or the log file gets lost for whatever reason. So if you don't know what the log file is at this point in time, don't worry, we will look at that in a separate video. Just assume you lose the database store. Just assume you lose the hard disk where the database store resides. Well, that's kind of a problem, obviously. So still we assume we are able to restart the database system. But then the question is, hey, on what data exactly do we restart the database system? Well, hopefully we have some sort of old copy, some replica, some archive version. If not, well, then you have a problem. Then you actually lost your database, and that might be super, super expensive for a company. If the data is the main asset of your company, the database of your customers, the database of whatever you do is lost, well, then this may be bankrupting your company. So it's really important to worry about that a little bit. So let's hope we can get back to some not too old copy, to some not too old archive of your database system. Then what you need to do in this situation is you have to restart the database system on that archive copy and then try to get back to a consistent state again. So it's a similar situation as in the second scenario. You proceed as in the loss of main memory, as above. It's the same algorithms. And then it depends, however, highly on the age of your archive, of your backup of the database system. How old is that? If you tend to do a database copy just once every week, well, then that's a copy you get back to. If you do a copy just once every year, well, then that's a copy you get back to, and maybe you lose everything in between. So this is really an important consideration you should make when replicating, when copying, when archiving your database system. We will get back to that later on and think about what is a good strategy in a particular situation. But before doing that, we will look at the concrete algorithms that are used in database systems. A very important technique has to do with logging, and that is what the next video is about. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!